Professor Suresh Advani, who is a professor of mechanical engineering and associate director of the Center of Composite Materials at the University of Delaware. He received his PhD from University of Illinois in 1987, and his main research interests are related to rheology, fluid mechanics, heat transfer, mostly applied to composite processing, and alternate energy sources as fuel cells and hydrogen storage. He has published more than 300 journal papers and delivered more than 100 invited lectures. He is also the lead author of a text on process modeling in composite manufacturing processes, and he is a fellow of the American Society of Mechanical Engineers. And also interesting for us, he is a North American editor of a well-known journal in composite materials, Composite Part A, Applied Science and Manufacturing. Professor Advani received recently the Outstanding Research Award in 2015 from American Society of Composites, and he served also as chair of the Mechanical Engineering Department at the University of Delaware from 2012 to 2017. Okay, please, Professor Advani.
Well, it's my great pleasure and honor to be here, and thank you all for coming. I know some of you have come from far distances, so I hope I don't disappoint you in my talk here. I've spent the last 3 days here looking at all the things you're doing here, and I'm really impressed, and I hope we get opportunities to collaborate in the future. So I'm very happy for extending me the invitation and looking after me here, so thank you very much. So today I'm going to talk something about which has been really an effort, ongoing effort to see all the things that we do in academia as to how, what we can do to help transition that into industry to move the composite manufacturing field ahead, and literally has been my goal. And you know, things are moving along, but they are slower than what I expect, but at least it's in the right direction. So before I start, just want to show you, tell you a little bit about my university and location. So we are located right between New York City and Washington, D.C., right in the middle here. And in fact, I heard yesterday we had a snowstorm, 9 inches of snow. So people were sending me pictures of how the snow is piling up. So I'm happy to be here. And it's only 2 hours away from New York and 2 hours from Washington, D.C. The university has over 18,000 undergraduate students and 5,000 graduate students. Our College of Engineering is one of 7 other colleges. This is Arts and Science and Marine Studies and so forth are the other colleges. So we are about 1/10 of the population. So we have about 2,000 undergraduates, 700 graduate students, and we do about a research of $90 million as a college. The college has 6 departments, like mechanical, electrical, civil, and so on, and 8 research centers. The centers don't give out degrees. They're just a place for people to get together and work. So one of the centers that I guess you're familiar with is the Center for Composite Materials, which has been around for over 40 years. It was the first center in the United States and has won a lot of Center of Excellence awards from pretty much every agency, NSF, ARO, ARL, ONR. And so because of the name and the reputation, we have a lot of industries that actually work with us. So the center not only does basic research, but it also does transfer of technology to the industry. So it's kind of a combination of your IRT and basic research all put together in one place, and it has its own staff to do that. And so the professors who are basically like me are paid by the university, but we work with the center, and there are many other faculty that work with the center and advise graduate students who get degrees in their own departments, but they work at the center and they use the facilities of the center. And then we have over 44 research professionals which are paid by the center, and they are the ones who do the transition work from academics to the industry. This is my research group from very early on, and only thing I'm going to present today is because of them. I mean, they have been the one who've been working. So 1991, you can see I look very young there and sitting. And this is in 2006. And this is my current research group. These guys have graduated. In fact, Tom is now working for IRT in Nantes, so he's there. And these are my current students who all look very happy because I'm not there. So anyway, so it's all because of them that you know we are where we are. So of course you guys don't need any introduction to composites, but basically what I'll talk about is mainly advanced composites. But I want to share a story with you about my early start in short fiber composites, which are again coming back. I mean, there is a lot of work being done in short fibers as well. So I guess the problem with short fibers was that you couldn't get them to be used for structural components because the fibers were not long enough to transfer the load from the matrix to the fibers. Many applications of composites, all lightweight, and it's more and more spreading in different areas. One of the things that I am excited about, but there is not much going on, and I hope there would be, is how not to design composites as black aluminum, not to take a composite. If you're going to replace something with a composite, just don't basically make it the same way. And a great example of this is the bicycle here, where because you can tailor the properties, you have fibers running along in this direction, you really don't need the third arm here. So not only do you save the material, but it's a better ride because you don't get as many vibrations as well. So this is something that is very underappreciated because there is not much out there. So I know that some of you are starting to build design and coupling it with manufacturing. Here's another example, like if instead of having it under your arms, with composites you can design it so that it is actually less material, more convenient, and these things can all come out if you can look at the load paths in a composite because you can tailor the properties. So first the story about how going from short fibers to continuous fibers. So in short fibers you usually have pellets and you have short fibers embedded in it, and then you put those pellets into a hopper, and then they go through a screw and into a mold, and you can make parts like this. And the advantage of short fibers is it's basically based on polymer processing, so you don't have to change the machines. They're very fast. You can make parts in 30 seconds, 1 minute, and so that's the big advantage. And the other short fiber composite process is the using SMC, where you have your resin and you chop the fibers in between, and then this becomes your charge that you take it to the place where you want to make the composite. You cut it up, you place the charge in the machine, and then you compress it. And you can make pretty large parts like that with it. So injection molding and compression moldings were very widely used for making composite parts, short fiber composite parts. Now, one of the problems with that is that here the fibers orient with flow because it goes as a suspension and the fibers can change orientation. And whenever there is flow inside, let's say a shear flow, if you're going this way in, injecting it from here, you'll get a lot of fibers aligned in this direction. If you go the other way around, then you have basically extensional flow in this direction because of the divergent section, and you get fibers aligned this way. So by changing the injection location, you have changed the properties of the part. And so So you have flow that affects the fiber orientation, that affects the microstructure, that affects the mechanical properties. And obviously, if all the fibers are aligned in this direction, you have much better mechanical properties in that direction as compared to the transverse direction. So the direction does play an important role. So very early on, we said, okay, we want to be able to predict the fiber orientation and flow. So this is an equation that was developed by Jeffrey in 1922 for a single fiber of how it rotates in shear flow. So P is the vector that points along the fiber, omega is the vorticity, epsilon dot is the velocity gradient tensor. And so he came up with this equation that allows you with time to see how this fiber will rotate. And most of the time the fiber spends its time aligned in the shear flow and sometimes at pole walls. So this was an analytical solution to this equation, and this lambda was the aspect ratio of diameter to the length of the fiber. So, but in composites, what we have is we have not one fiber, we have lots of fibers. So taking a single fiber equation and saying, okay, this is the orientation is not really the answer, but although we have a solution in that case. So early on, I developed an equation to describe the orientation state. So basically, instead of describing the orientation of one fiber, we describe the orientation state with the orientation second order tensor. So the tensor gives you the orientation state. And it's also very nice because if you want to find mechanical properties, your elastic modulus can be a fourth order tensor, so you can actually use the orientation state to get those values. And so this allowed us to actually predict the orientation state from flow. So you see there are very similar things that were in Jeffrey's equation, but it is now extended to an orientation state, and we introduce what we call as a fiber-fiber interaction parameter because the fibers are close to each other and they're going to interact. So this interaction coefficient is going to depend on fiber volume fraction, it's going to depend on the concentration, and so forth. But it's a phenomenological parameter. We don't know how to find this from first principles. But we could come up with experiments to characterize it and so forth. And then we can predict the orientation of fibers in a flowing suspension for short fiber composites. So the reason I showed you this was a story I want to tell you that has become my philosophy that my advisor told me many years ago. So the story is that there are two people here looking for something under the light. And this person comes up here and says, "What are you looking for?" They said, "We are looking for our car keys." So he says, "Okay, I'll help you." So he also starts looking there. And then after a minute, he asks the question, "Where did you drop your car keys?" And they say, "Well, we dropped it next to the car." So they say, "Why are you looking here?" And they say, "Well, there is more light here." So that's why they're looking over there. So, if you use Jeffrey's equation to solve composite problem, yes, you have the solution, but that's not the right solution, and you know that, but you still do that. And you see a lot of scientists doing that. What they do is they're more comfortable solving problems that have closed form solutions and so forth. They may not be the right solutions, but they do that. So the question is to ask the right question. Don't be afraid to look in the dark and move your light in the search space. So that's basically the message I got, and that's what I've been trying to follow in my research. And actually, the theory we developed, it was really nice to see that theory. There are two computer programs now commercially available, MoldFlow and Mold X3D. They both use our theory, the method we developed to look at fiber orientation in injection molding components. So there are, they literally use this. And of course, we have to come up with this interaction coefficient, but they find that, they are able to make better predictions. So that had a good end of the story. And of course, thinking about applications, early on, I looked at this application where when you have shear flow, you can align the fibers in the neck region. So when you look at a hip implant, that it's a very, very crude operation when people break their hips, or when you get old, you need to have a hip replaced. You have like a ball, and then you have this titanium implant. And the problem with titanium is it's too stiff. It is strong, but it's too stiff. So the load transfer is to a point and not distributed. So the bone around here does not take any load, and so it resorbs, and your hip implant will fail. And there is, every 20 years it fails. So the question was, how do you make it stronger? The idea is to use short fiber composites where you can tailor the stiffness so that the load can be distributed. The only area which is a problem was the neck. So if all the fibers align along the neck, you can actually have that strength. So this will be a better implant than the titanium. But of course, this idea didn't go very far because we didn't get any funding for this. And so, and people, I guess, there's still some people working in other countries on this idea. Okay, so that was my short fiber composite story. So after I moved to Delaware, after a while I started working in continuous composites fibers, where you have, the main area is basically when you have dry fibers and you infuse the resin in some form to make a composite. And there are fibers that come in various forms, and there are different resins. And very early on at our center, we had these three guys who are very famous in the mechanics of composites, Roy McCullough, Suresh G, and Jack Vinson, who were working on looking at how to predict the properties, the structural properties of the composites using micromechanics and so forth. And then around when I came, there was Byron Pipes, who was saying that, he came from Boeing, he worked for Boeing. So he said, in Boeing, they're all using trial and error. There is some science in composites, and we should try to, address the science part in manufacturing. So, there are many processes, and we have been trying to develop, models and simulation based on scientific principles for this. And the whole goal was basically that in short fibers, you don't have great properties, but it's very easy to process. In continuous fibers, you have great properties, but it's very difficult to process. So the goal was to try to improve the processing of continuous fibers using a scientific method. And my personal goal was, can we break the ball between manufacturing practice and what we do in the lab so that we can build process simulations that can be used directly in the manufacturing practice. And although it's two different languages that people speak here and here, we can build interfaces that can help bridge the gap. And I see that a lot of you are already doing that here. I work in all these areas, but I will just talk today about just the ones that I've highlighted a little bit here in the interest of time. So, there are many composite manufacturing processes such as tape placement, you have sheet forming where you're trying to form the composite, pultrusion where you're continuously drawing the fibers. And then you have the infusion processes such as RTM and WARTM, which is what I'm going to focus on. You also have the autoclave, out of autoclave process, compression molding. So there are many, many different processes, and the main goal in all these processes is to reduce the defects, improve the time scale as to how fast you can process, and reduce the variability. Because composites, because they are heterogeneous, there can be a lot of variability in the properties. So those are the basically three goals that you do. And one of the things I did on my last sabbatical, I didn't go anywhere. I stayed in Delaware, and I basically worked on a book to write about the science base of these processes, and I divided them into three ways. You have the fiber suspension flows where the resin and fibers flow together, squeeze flow where you have in thermoplastics where the fiber and resin also flow together, and then for thermosets or for thermoplastics that with low viscosity that polymerize later on, you can have basically fibers where the resin actually moves relative to the fibers, and it is more modeled as flow through porous media. So that's what I will talk about today. So the two main common processes of liquid composite molding are resin transfer molding and vacuum assisted resin transfer molding. So the big difference is in resin transfer molding, you have two rigid molds. You infuse the resin from a gate, and when the resin comes out at the vent, you close the inlet, you let the resin cure, and then you open the mold, and you hope you got a part without any dry spots. In vacuum assisted transfer molding, you do not have the second rigid mold, but you have a bag that covers the mold. So the only pressure you have to work with is 1 atmosphere, where the resin comes in at 1 atmosphere and you have vacuum at the other end. And when the resin comes to the vacuum port, you close the inlet and you keep the vacuum until the part cures, and then you take your part out. So what happens in these processes is that you can get big dry spots like this, and because it's a thermoset resin, you have to literally throw away this part, because once the resin cures, you can't do much. You can also have micro voids, inside the toes, or you could have voids where you have flow fronts where they meet. So you could have voids inside the toes, around the toes, dry spots, and the key is to be able to get rid of all of these. So very early when we started, we said, okay, let's first address the macro problem, because right now there is only trial and error, and so any effort we can spend on helping the manufacturing practice, it will be really good, so that we don't get parts like that. Because once you close the mold, you cannot see inside, so a simulation would be very, very helpful. So what I'm going to do is I'm going to talk about the process modeling on 3 scales: the macro scale, where you get to predict these big voids, and also what can you do in the process to optimize, to control the flow so that you do not get things like this. Mesoscale modeling is when you have resin that flows faster in between the toes and not inside the toes. So you have a dual scale flow. So how do you get rid of the voids in that case? And then micro scale modeling, when you have flow between fibers and the capillary effects that become important. So first, the macro scale, it was the governing equation was Darcy's law. In 2D, you would write down average velocity is proportional to the pressure gradient, and the proportionality is basically the permeability of your material, which you have to characterize because that comes from as an input. And the difference from normal Darcy's law is that it's anisotropic, so I could have different resistances in different direction, which I can express with this permeability tensor. So when I take this velocity field and I apply the mass conservation, I get my governing equation for the pressure. So all I have to do is solve for the pressure with some boundary conditions. The boundary conditions could be at the inlet, what is the injection pressure, what is the flow rate, and the flow front boundary condition of what is the pressure at the flow front, and no flow out of the mold walls. If you have sealed your mold properly, that flow velocity will be 0. And then what you're doing is you're applying this equation with the boundary condition and you're solving for the pressure in here. The problem is that it's a moving boundary problem, so at each time step you have to change your domain because more resin is coming in, and then you have to resolve the problem. So what we do is you solve it as a steady state problem at this time step, then you advance the flow front once you know the pressures, and then you resolve it as a steady state problem. So one of the other advantages of this is that when I do it that way, I can change my permeability, I can change my resin pressure at the next time step, I can change whatever I want when I go from one time step to the next time step. So although it's a time dependent problem, it's a quasi-steady problem where I'm solving it at each time step. I'm solving a steady state problem. And this is completely okay because the momentum transfer, because of the viscosity, is instantaneous, unlike water where you may have some inertia effects. Here there are no inertia effects. Now, of course, you can extend that to 3D, and then now instead of having to deal with 4 values, you have 9 values to deal with when you're doing this. The nice thing is at least this, hopefully this, well, we have proved this. So this is a symmetric tensor, so you only have like 6 values to worry about that you have to calculate. And the reason you need to solve 3D in Vartam is because usually in Vartam you put a distribution media on top, which allows the resin to go faster on the top, and so in reality through the thickness you have a 3D flow, so that's why you need to solve it as 3D. In RTM usually that is not present, so you can do it as a 2D problem. Okay, so what we did was we came up with the way where you don't have to remesh. You make your mesh the first time of your part, and it could come from the design aspect where people are designing the mold, they can mesh it. So once I have the mesh, I can solve for the pressure field in wherever I have the flow inside the mold. So initially I may have flow just in one node that has just come in, and I solve this equation just in that domain. Once I know the pressure, I associate a fill factor with each node, and I update the fill factor. So initially, wherever there is resin, the fill factor is 1. Wherever there is no resin, the fill factor is 0. And as once I find the pressure, I can calculate the flow rate that goes from one element to the next element, and I can update the fill factor. So at the next time step, my domain has changed because the fill factor that was 0 or less than 1 has become 1. And so that way I can update my filling domain. So that's how we solve the problem. Now, one important aspect is the permeability. We still need to know those permeability values. So very early on, we built a setup where we inject the resin into the fabric. So what we do is we have 2 see-through plates where we put the fabric in there. We inject the resin from the bottom into the fabric, and we had camera at the top and camera at the bottom. And by image analysis, we can match how the flow front is flowing at different time steps. And from that, we were able to analytically calculate the permeabilities of various fabrics in the X direction, in the Y direction, and the Z direction. And what I want you to note is that in the Z direction, the permeability can be 2 orders of magnitude less in the X and Y direction. So even if you're sending the flow really fast in the top plane, it is infusing in the lower planes much more slowly. Once we have the permeability values, we can run simulations, and over the years we have done many validations. This is a 6-foot by 3-foot part where we injected the resin from here, and we were able to map the flow fronts to what we saw in the experiment. Here are some other ones with different fiber volume fraction, and you can see the experiment on the left, the simulation on the right. Here you have race tracking along one edge where the resin is going faster, and we are able to even capture that. Here you have race tracking along both the sides. So we've done many of these validations, and this is for a 3D part which had actually ribs and ply drop-offs, and the resin to come at the end was over here. So you would get a dry spot, and then again in our experiment we were able to predict that. Again, this one was a 6-foot by 3-foot part, so not a small part on which we did validation. And we can do very complex structures. So one of the beauties of the simulation is because the way we do it, it's very fast. So to simulate something like this with 10,000 nodes on a PC, it takes about 10 minutes. So we can do a part with 10,000 nodes in 10 minutes. So it allows us to do optimization and look at different probabilities and so forth very quickly. So that was at at this point I should have said, okay, work done, let's stop working in this area, move on to the next area, but there were still problems. So the one nice thing about working in a center is that the industry comes in and tells you what their problems are. So as an academician, you try to think about how to address that, because that's the challenge, right? So here, of course, the problems are, they're saying, okay, you can do the dry spots, but when we take a micrograph of the part, we see that we still have like porosity inside, between the toes or inside the toes. So what that told us is that really we need to model, this is a dual scale porous media. The resin comes in faster in between the toes, and then it's impregnating the toes. So we decided to say, okay, how do we address that? So here is we did some experiments where you inject the resin, and notice how it's all dark here, but you have some white areas. And so the reason is the toes are still filling. So the resin is coming in, and so initially we were modeling it like this. The toes are filling at the same time as around the regions, but in reality what's happening is the resin is going further and these toes are filling later on. And so if you don't fill those toes, that's your porosity, right? So we decided to do multiscale modeling, where what we do in our existing mesh, and again, we wanted to do it in a quick way. We don't want to, remember, if I can give the industry 80% of the solution, they're happy, because right now they have 0% of the solution. So here we said, okay, let's assign one-dimensional elements to our mesh, and these one-dimensional elements represent the fiber toes. And these toes will have their own permeability, which will be different from the bulk permeability that you measure in the experiment. So they will have a much lower permeability, and we can actually calculate the volume of the toes, so we can have a separate volume fraction for the toes. And now we can use the same simulation with these additional elements. The only price we have to pay is we have to introduce a second permeability, one that is with the toes for these elements. So now if I inject the resin here, the red area is where the fill factors for one-dimensional elements and for two-dimensional elements is 1. That means they're all filled. Between the two black lines is where you have the regions in between the fabric that's filled, but the toes are not completely filled, and then this region is completely where there is nothing filled. Okay, so what is the advantage of doing it this way in a manufacturing practice? What I want to do is I want to keep injecting the resin not when this line arrives here at the vent, but until this line arrives at the vent, because that will ensure that my toes are also filled. So what I would do is I would let the resin bleed, just let the resin go to waste a little bit till this line arrives here. So the simulation can tell you how long do you have to wait before you shut off your injection. So of course the other thing is, how do I find this second permeability? So we came up with an analytical solution for a dual scale porous media. So what happens is, when you have a single scale porous media where the toes and the resin along the toes are filling at the same rate, the pressure, if you inject at a constant flow rate, the pressure increases linearly. Okay, that will tell you it's a single scale porous media when you do this experiment. If you have toes that are filling a little bit later, the pressure is not a straight line, but it has a little drooping effect, because the resin is still going into the toes while the flow front is here. So when you have a pressure profile at the inlet that looks like this, when you're injecting at a constant flow rate, you can use my analytical solution, which has the bulk permeability and the toe permeability, to match your experimental profile with your inlet pressure here by changing the bulk and the toe permeability. Now usually the bulk permeability is the slope very close at the inlet, so this value you can find immediately, and then you keep changing the toe permeability until they match. And so from one experiment you can get both the values of the bulk and the toe permeability. And then you can apply this methodology to, we did a simulation of the hood where you inject it on the Dualscale, and you find that this is the region that is partially filled when the resin reaches the final vent, and that is after an hour and a half. And then I have to continue the simulation for another hour and a half to make sure that that other region gets filled. Okay, so obviously it took twice the amount of time, and I wasted some resin, but I was able to saturate the complete thing. Now we also came up with a way to reduce this time, but what you do is at the vent you put in some resistors so that you make the vent very small, so you build up the pressure near the vent, which will allow the resin to go into the toes much faster, and then you can also model that and show how you can reduce that time. Okay, so that was one other thing that happens, is that as you can see, hopefully the video will work, but there is a resin film on top, and as you compress that resin film, you notice that the resin comes in through those pinholes and then starts to spread into the toes. And again, that has the ability to capture the voids, and the size of the pinholes will again introduce all the variability that happens in here. So as you can see in here, that if I take a fabric and I take a picture of it, these are the pinholes through which the light is going. And notice that no pinholes are the same size, they are not everywhere, and this is the variability that you're introducing in your composite processing. And what happens is if you have a distribution media on top and you're watching from the bottom, you notice that, if you put in a distribution media where the resin goes really fast on the top, you end up with dry areas in here, okay? And so what we did is we said, let's see if we can model this. So we actually started introducing a stochastical way of modeling it. So what we do is basically we can put in pinholes. So this is our distribution media on top. These are our fabric layers, and I can put pinholes at different locations. So by taking a picture of my fabric, I can use a Gaussian distribution or some sort of a distribution to lay down the pinholes, and then I can look at how the flow from the distribution media is going through the pinholes. So here the pinholes are laid randomly, and you notice that if you have a distribution media that is very, very permeable, which means this is the most permeable distribution media, you get the spotting effect. The blue is when the resin arrives first, the red is when the resin arrives last. So you're going to get, dry spots in here. If you make your permeability of your distribution media 2 orders of magnitude less, you see the flow front at the bottom layer is moving more uniformly. So this is again counterintuitive. You tell the person in manufacturing practice, hey, don't use a distribution media that is highly permeable, you'll get a better part. So what we learned from simulation, we were able to transfer it in a few words. They don't have to run this simulation. Okay, so now on the microscale level, what happens is usually you put a drop of resin on a toe, and this contact angle plays an important role of how quickly this is going to go inside the toe. And so, you can measure the contact angle very easily, and there is some law of what happens at that level. So one thing to mention is that the capillary pressure between the fibers is only important where you have vacuum, because capillary pressure is very low. If you have a pressure that is, it's usually about 1/10 of the atmospheric pressure. So it is only going to play an important role near the flow front. And this capillary pressure will depend on the distance between the fibers. So if I take this third fiber, so this is one fiber, this is the second fiber, this is the third fiber. If I move this fiber away a little bit, my capillary pressure can change dramatically. So when you look at a toe, and if the toes, the fibers are not uniformly arranged, so the capillary pressure inside the toe is not same everywhere, it's different. And that's what we can show from here. And it also depends on the contact angle of the fluid. So if the contact angle is small, your capillary pressure is higher, and if it is high, then the capillary pressure is smaller. And as I said, it is important more near the flow front and not here, because the pressure is much higher here. And so that's where it is important. And as you can see, the effect of contact angle, you put a drop, takes 24 seconds to go in. It may take longer if it was less wetting fluid. So this also has advantages in, for example, in additive manufacturing. So here is a case where you have a fiber toe, and that's going through inject printer, where you can actually drop a fluid onto the toe, and you want to see how it spreads into the toe. So you drop it over here at time t equal 0, and you see it spreading a little bit. And then when you introduce the second drop, you see the interaction between the drop within the time scale. So it will give you an idea about how fast you should move your toe, how fast you should drop it, what should be the size of the drop, and so on. So we can model that with our own simulation. And the other thing at this level it can tell you, as I said, these fibers are kind of separated not uniformly. So the capillary pressure is going to be high here, but not in this region. And if you keep the capillary pressure the same everywhere, or the distance between the fiber the same everywhere, and you introduce the resin from the outside, you'll find that your void is this blue area is right in the middle. However, if you introduce the capillary pressure, which will be different in different locations, and now this has been denoted here by fiber volume fraction in the toe being different inside the toe, you notice that the voids are not like this, but they are spread out, which is what is observed in practice. The voids are never in the center of the toe. And so this tells you that, okay, if you can get the voids to the edge of the toe, you can vacuum it and get them out, and then you can stop it from having voids inside. Okay, so that was modeling at different levels. Now, how does material and process variability kind of introduce more problems for us? So the one very, very common process variability is the race tracking. When you put the fabric along the walls, you will get some channels, you'll get some little areas here where it's not completely flush, so there will be a gap. You may have ribs that are cut too short, and all this will cause the flow to go faster in that region. And you can either have weak race tracking or strong race tracking. So it's practically impossible to have no race tracking along the edges when you cut a fabric, because even if you cut it really well, the resistance here is going to be different than the resistance here. So there's always going to be a higher permeability in the gap than in the bulk region. And you can see this. This story is again from ARL lab, which basically they were trying to make this 40-foot keel beam of the helicopter by RTM, and then they found voids in the bottom. And they did not use any simulations or anything like that. They just designed the mold, they did it, and then they tried to fix it by putting some unidirectional fabric to get the resin to go in here. And after making 2 attempts, they decided, or I don't know how many attempts, they decided that they should just go back to the autoclave. I asked them to provide me the part much later on, 2 years later, and I just put some race tracking along the edges. I just said the resin flows 5 times faster in these gaps than in the bulk, and I was able to predict that the voids actually will occur in the bottom, because this is the region where the resin arrives last. So they were really very impressed that, even with not having much information, we were able to give them some answers. And this is another example which shows you, how around the corners the race tracking happens. And so simulation is on the right, and this is the experiment. And so many other examples of race tracking, like when you put inserts inside the mold, you can have race tracking. And what happens is when you have race tracking, if you don't include that in your simulation and you say, okay, the vent is here, and then what happens is if you have race tracking, the flow goes faster there, goes past the vent, and even if you're letting the resin bleed, you have trapped this air and you can't get that air out, and you'll get a void there. So I said, okay, is race tracking that is something that is predictable? So this is the advantage of being in academics, in academia, is that I had 5 students do 10 experiments each, where they put, there was race tracking along these 5 edges, 1, 2, 3, 4, 5, and we injected it from the 2 sides, and here is the mold, and we had basically sensors in different locations to see when the resin arrived there. And here are the results at those 5 edges by the 5 students, and this is the average of their 10 experiment. So at each edge, the race tracking was different for each student, and you could probably look at this and see which student was more careful and which student was less careful, but so this is the average of 10 experiments. It's not just one experiment that they did. So what it told us was, you can't fight race tracking. It's going to happen. You can't have skilled labor that's going to do it. So instead of fighting it, let's figure out, when we have race tracking, what is the great place to put the inlet and the exit. The other thing we talked about was when you have these pinholes, and they can be, again, different for different fabrics. So this is the pinhole distribution in this fabric, the diameter of the pinholes. And you can see, because of those pinholes, you get these sort of flow fronts at the bottom, because the resin, when it comes from the top, wherever there is a pinhole, it comes to the bottom and then starts to spread around. So we have to be able to even address those kind of issues. Okay, so how can we do that? So some examples. So first case we did was, okay, let's do passive control. So what is passive control? Okay, so I want to make this part. I have high fiber volume fraction in one place, low fiber volume fraction in another place. I could have race tracking at the top. I could have race tracking at the bottom. So what I do is I say, okay, let me look at all the combinations of race tracking, run the simulations for all of them, okay? And then find out, what is the best way to put the gate and where is the best way to put the vent. So here's an example. So if I have a gate here and I have race tracking along these 3 edges, and this is the distribution of race tracking, which means most of the time I will have low race tracking, some of the time I will have high race tracking, and I can assign a probability to it. And then I can run the simulation so that I have 4 types of race tracking here, 4 here, 4 here. So I have 256 scenarios. I can run 256 scenarios. I can weigh them by their probability, superimpose all of them, and then figure out the probability of where the resin will arrive last, and I can put the vents over there. So here's an example where I have this mold where I have channels, 2 channels, so the race tracking can happen along the channels and along the top and the bottom. So there are 4 discrete values of race tracking, from no race tracking to weak to medium to strong. So, and you have 5 edges, so I have 1,024 scenarios. So I run all the scenarios through my method to see where I should put the vents. And look at this, it's not intuitive. You would put the vents over here. The intuitive, if you had 3 vents, you would say, okay, put it where the first insert is, the second insert is, and at the end. That would be your intuitive based design. This is based on accounting for the race tracking probabilities. And what we did was we ran 1,000 simulations with random race tracking along the edges. This was successful only 28% of the time. This was successful more than twice the time. Not 100%, but it improved the probability. And this was a passive control. You didn't have to do anything, in terms of the manufacturing practice. So now here's another one where the distribution media, usually what people do is they just put the distribution media on the top, they cover the whole thing, maybe they leave a little gap so that the resin just doesn't go into the vent. But what if you had ribs along here? So they'll say, okay, just cut it along the ribs and put it over there and then see what happens. So if you put the distribution media like that and you run your simulation and your vent is over here, okay, at this point, so you will see that the resin arrives at the vent much before it fills this region. And all I made is a small change here. I say, okay, just cut the distribution media all the way to the end, so that now the distribution media is not here, and I introduce the inlet at the same place, and you notice that that small change in the distribution media design will allow the resin will arrive at the vent last, and you'll get a good part. So the difference between a good and a bad part is so small. And this is something they can easily introduce in manufacturing practice. But the question is, how do you design this? So one way is to come up with a methodology. So that's your scientific part. You kind of come up with, okay, how do I design it in a scientific way? How do I assign a permeability map to my distribution media? So what we did was, here is your trailer, the trailer geometry. I could have race tracking along all these edges. There are 10 race tracking channels, and I can divide them. So what I do is I take my mold, I divide them into different regions, and then I add or take away a region, and I simulate the flow to see which gives me the best result. So this is our scientific part, which became a paper of how we do that. And basically what our method tells us. So here we keep running the simulation over and over again by changing the map of the distribution media until we can fill, despite the disturbances, we are able to fill the part without any voids. And our method told us that put a distribution media that looks like this and not the whole way, put it this way. And again, you'll say, how would you do that in manufacturing practice? It's easy. You can cut the distribution media and attach it to your bag that you use to cover the mold. And then so it's not like you have to have some special skills. And you do that, and then now you find that you have possible 1,024 scenarios that can take place because of the 10 race tracking channels. And in all cases, with that distribution media design, we were able to fill the part. Whereas if you had the distribution media covering the complete surface, there were many times when you were getting voids, and those would be your rejects. You would have to throw away those parts. And today, the manufacturing practice is such that people build into their cost price some amount of failure. So they know that they're not going to make, if they have to make 100 parts, they would build them for 150, because they know some of the parts will not be manufactured properly because of these variations. Okay, so how do we go from something that is passive to something that is active control? So the way you do that is you say, okay, I'm going to put in sensors into my mold, and the sensors are going to tell me what kind of scenario is taking place. And once the sensor tells me what kind of scenario is taking place, I am going to identify what that disturbance is, and then I'm going to use an active control, have an actuator that can steer the resin in the direction I want it to go, okay? And that way I will always get 100%, and this can be automated. So this could become a part of your equipment. And this was done under an ONR program where we actually used the simulation to figure out where to put the sensors so I can figure out which scenario is taking place, and then I can run offline the scenarios and design a control action, and once I know which scenario is taking place, I can put the right corrective action. Okay, so I know this is not very clear, but basically let's take an example where I have a part with an insert in here. So I can have race tracking along the three edges at the top and the bottom, either weak or strong. So I have two levels of race tracking, weak or strong. So I have 32 scenarios. So I run my simulation, I find out what are the 32 disturbance modes that can happen, and then beforehand I decide what is the control action I can take that will be able to counteract that disturbance and give me a good part. So this is all a database that I've already stored. Okay, and my simulation tells me where I should put the sensors so I can identify which of the 32 disturbances are taking place, and very early on, so I have time to take control action. If it tells me at the end, I can't do anything. So, and then I have two auxiliary gates. So I introduced the resin from the two sides, but I also have two auxiliary gates here and here, and my vent is over here. So the goal is to try to push the resin towards the vent based on which scenario is taking place. So I will show you, like, if you didn't use any control, for example, and if there was race tracking along here, the resin will reach the vent and you'll end up with a void here. If you use the control, you will open this auxiliary gate and you'll push the resin towards the vent, and you'll be able to get a good part. So as you can see in the experiment here. So I'll show you here the actual simulation. So here in the top, these are where we have the sensors, and of course here we don't take any control action. So whatever scenario is taking place, if I have race tracking along here, once the resin reaches the vent over here, I won't be able to fill this completely. Now here with the control action, the sensors say, okay, it's scenario number 29 that's taking place, and the control action is to push when the resin reaches this sensor, push the resin with this auxiliary gate towards the vent, and as you can see in the experiment and in the simulation, it pushes it towards the vent, and you're able to basically fill the part. So now the good thing here is the worker does not have to know where the race tracking is taking place. They just cut the preform, they put it in the mold, and the system will identify what is happening. So we did this 14 times, and every time it was a different race tracking scenario because our sensors were telling us what race tracking scenario it was. And out of the 14 times, 12 times it filled perfectly. The 2 times it failed was not because of a control action, but because the sensors failed. So what it told us was you need to put in redundant sensors into the system. And so the nice thing about that is we call this intelligent manufacturing, but basically what it is it's sensors and simulation based. So you have a part like that, you design your mold, you design the interface of where to put the sensors, where to put the auxiliary gates, and then you basically build it into your system so that you get a good part every time. Okay, so that was in RTM. Okay, in RTM you can do that. Now what about Vartum? I can't push the resin because once I start pushing the resin, the bag will just go up, right? Because it's under vacuum. So you do the reverse. We have a chamber that can apply a vacuum anywhere, or it can, let's say, it can relax the vacuum. So what happens is, by relaxing the vacuum, you increase the permeability of the fabric there. So the resin will always go to where there is, less resistance. So we actually build a setup where we would look with a camera as to where we want the resin to be, and then we would say, okay, we want the resin to come here, so then we will have a chamber that will sit here and it will kind of increase the permeability and steer the resin over there. So we actually built this system where we could actually connect the lab view and the limbs, and this was online. So what we'll do is from the camera, we'll say, okay, this is where the flow is. We'll convert that into a mesh, and we'll run the next 2-3 time steps to see where we want our chamber to be, and then we'll give that instruction to the chamber, and the chamber will go out there, and that's how we automated it. So I'll show you this where it was fully automated. It's a simple example, but basically you could have race tracking along here or here, and the camera notices it, and then it tells so you can see that the resin is coming in, there's race tracking, so the chamber goes there, so the resin goes there, and you can see the chamber moving to where there is no resin and allowing it for the resin to flow over there. And as I noticed in your IRT, you had a robot that was doing the painting, right? So you can use the same robot to do something like this, where you can actually guide the flow in a Wharton process based on some of the things you see. So this is my real dream in the end, is that basically, you design a part, you figure out, how, where you want your, you take your part, you design it, you figure out where you want your vents and your gates and how you want to control it. And then through lab view interface, you can just connect that and make a good part. So that is every time. So, and you can build it into your machine. So, bringing the scientific understanding to a point where not every person who's working on the shop floor has to know what is behind it. It can be a black box for them. And so this is my last slide. So some of the remarks I want to make here is that macro voids happen because of race tracking along the corners and edges. Micro voids due to dual scale and maybe some volatiles. I've shown you that flow simulations can be used to prevent these voids with proper injection path design and introducing flow control. So these simulations can actually eventually help in developing automated manufacturing systems and platforms so that you can improve the composite manufacturing and reduce the cycle time. Thank you very much for your attention.
Thank you very much, Suresh, for this very pedagogic presentation. I guess that people who are not convinced before your presentation of the importance of process modeling have now a good view and insight of what can be done using such kind of modeling for process optimization. Okay, please feel free to ask some questions to Suresh.
Thank you very much for your presentation. Are you able, as an output from your simulation, to give this as an input? So you didn't speak about it, but to behavior laws, deformation and failure simulation. Are you able to take output from your simulation and provide them as an input to other simulation and able to predict the complete chain from process modeling to material simulation, virtual allowable simulations?
I mean, in principle, this could be done. The part of the problem is getting the right platforms together. What we have been able to do is actually, I don't have the slide here, but what we are able to do is when somebody is designing a CAD part, of what they're looking for, in the background, we can create a mesh and run the simulation and say, okay, this is not going to be a good filling. You may get a void here. Maybe you can relax the corner here, or you can do something somewhere else. Give that feedback to the designer. So the designer is not just designing the part and throwing it over the fence, telling the person to manufacture it, but at the same time the designer is getting some feedback as to how easy it is to make that part and so forth. Now, what your question was, okay, now once I do the simulation, can I take this and feed it into looking at damage and other things? It's possible because we can predict the microvoids where they are, and then that information can be put in the same stress analysis to the platform, and you can do the stress analysis with those void locations to see if that void is going to be detrimental for your part or not. And for example, in injection molding, they do that in the sense that when you have the flow fronts that come and meet, the fibers cannot go across the flow front, so you have a knit line. So they try to put the knit line in a place where it is not going to be structurally crucial. So you could do similar things over here too.
Can you predict also the fiber disorientation, the disorientations during the process?
The disorientation of what? Of the disorientation of what? Okay, so in this process, usually you have a fabric and the fibers are continuous, and they usually don't change orientation. So it's the resin that's flowing in between the fibers. But in high pressure RTM now, there is an issue of fiber washout. The pressure is so high that you could actually have some fibers that kind of move aside, and they can create larger defects like gaps, which is what you're referring to. Those gaps can be detrimental for your mechanical properties because that's a real defect then.
Other questions? I have one. Here in your presentation, you mainly focused on R2M processes, liquid injection processes. Have you also some kind of works on, for example, prepreg processes or thermoplastic prepreg consolidation processes?
Yes, yeah. I have a complete other talk on consolidation of prepregs in basically in out of autoclave processes, and I can summarize a little bit of what we discovered there through our processing science. Is that so when you do something in the autoclave, you apply a lot of pressure. And because you have a lot of pressure, you can prevent the volatiles from growing, and so your void fraction is very low. In out of autoclave, you have only 1 atmosphere pressure. So you only have 1 atmospheric pressure, so you tend to get more volatiles. So what we discovered that in the out of autoclave process, if you use prepregs that are not fully saturated, that have pathways, air pathways. So what you do is you put these prepregs inside on your tool surface, you put the bag, and then you draw a vacuum. And the key is you want to be able to get all the air out from in between these plies. And if you do that, then if you apply just 1 atmospheric pressure, you're able to consolidate the part. But to be able to get that air out, you need continuous pathways. So what we discovered was that using prepregs that are not fully saturated is actually better for out of autoclave process. So we developed a model for how long do you have to keep it under vacuum before you put it in the oven and start to increase the viscosity of the resin so it can flow. And so what happens is most of the time they don't wait long enough. And so this was about how do how do we predict that? So that's the part we have looked at.
Okay, thank you. Quentin?
Okay, well, thank you for that very nice talk. Wanted to ask a question about the Dualscale permeability. And you have a model that gives you a permeability of the fiber bundle, but this seems to be just a 1D permeability. And but we know that flow will be different in the length of the fiber or transverse. And do you have a method for getting a 2D permeability for at Dualscale?
It's a good question. See, the reason we just looked at just the transverse permeability, because along the flow you're going to have some capillary effects and other things. There was no real easy way to figure out what that would be. Now we have done separate experiments, like what you do is you can take your toes and you can just put it inside a bath, and then you look at how far it rises, and from that you can figure out what the permeability of the toe is. Not very accurate, but that gives you the permeability in the longitudinal direction of the fibers. But with that technique, we had to make the assumption that it is isotropic in both directions.
Okay, other question? No more question? Okay, so I would like...
Yeah.
There is one? Okay, sorry.
I was curious about 3D RTM actually, because I know Hatice tried before, and I was curious about her results. I mean, your PhD student. In terms of 3D RTM, what do you think is the most challenging thing? Because we are talking about macro scale and micro scale, and I believe like the fiber architecture is not the same, so there should be some like a randomity. I don't know what you think about this actually. My question is a bit broad.
Yeah, I see what you're saying. So the 3D RTM is no different than doing the 2D, because it's really, all I need is more permeabilities, and the mesh will be a little bit bigger, but it can be done. The only problem happens is on a PC it may be an issue, because if you have 100,000 elements or 200,000 elements, then you don't have enough memory on it. But nowadays you can add memory chips to your PC, so you can increase that. I think maybe what you're referring to is that what I was talking about, having pinholes. When you have different pinholes in 3D, you can model the pinholes, but the question is, how do you describe how the pinholes are spread out? So my next PhD student after Hatice has been actually working on that, and we find that it's basically a Gaussian distribution of pinholes, and that allows us to run multiple simulations, capture how much voids we are getting, and then figure out what is the best distribution media permeability on the top that will allow us to reduce these voids.
Okay, yeah, exactly. That's what I was talking about. Geometrical distribution of the holes, and of course, like the structure of the fiber, because it's completely different. Okay, thank you.
Okay, perhaps a last question. All your simulations have been done with a software you have developed in your own research center, I believe.
Yeah.
And how do you interact with what you found and what you have implemented in this software with what is available in the commercial software? Have you some contact with companies who are developing commercial softwares, and how you interact with them?
Yeah, so it's a good question, because I really want companies to use this, right? The hard part for companies is the learning curve, okay? So even if you teach them how to use the software, they always have, there is some resistance on them. They always come back to you and say, oh, you just do the part for me and tell me the answer, So obviously we don't have like, technical help like other commercials companies do have. So in the meanwhile, when I started then of course we have, I guess ESI came out, and they do very similar things, and they have technical help. The difference, as I see, between them and us is that our software is very open-ended, so it can be used for research problems, like the Dualscale, doing control, doing optimization, and so we do a lot more other than here is a part, where should be the injection, where should be the vent. So it's more, a student can actually take it and with very little time, learn how to use it. An industry person, on the other hand, will need a lot of hand-holding on, in terms of, it's not running the simulation, it's how do you take a CAD drawing or a CAD platform and integrate that with our simulation, which ESI can do because they have a CAD profile and they can, they have developed that same profile. So we have worked with MSC and some other people to do that, and it can be done, but it's not easy. So just recently, maybe 2 years ago, I decided to actually, because we gave a license to, exclusive license to Convergent, which is, they do Cure Kinetic software. This Anush from British Columbia, he has a company, and he has many people who work on this. So they are going to try to play the role of interacting with the industry with our help, a little bit of our help, but they have 70 people that can do this. So that's how I'm trying to sort of link up with the industry. But what I'm finding more and more is that it's the small and medium scale industries that need the help. And they really don't have the expertise or the learning curve. So how can we take the knowledge from this and distribute it in a way that they can use it? And I don't know the answer to that, but I think that would be a very good thing in countries like US, France, Germany, where you can have maybe some engineers, a place where small and medium companies can go for help when they have an issue.
Okay, thank you very much. As a matter of fact, most of the parts, which are not huge parts, are manufactured by small and medium-sized companies, and they have, in general, not the skills in-house to be able to use such kind of softwares. Okay. No other question? So I thank you again, Suresh.
Thank you again for coming.